Hi, everybody. Welcome to Orgoland. Evidently today we're skipping out of Orgoland a little bit and going to acid base land. Ooh, cold sweat. No, it's okay. Because really the goal of this is not to teach you everything that you need to know for every acid base reaction you've ever seen in your life, but just enough to get you through Orgoland comfortably and successfully as you go through your tour of Orgoland, wanting to know what is an acid and what is a base. So this is one lecture that's divided into two. This is lecture 3A, and I definitely hope you take a look at lecture 3B. Okay, so let's start our journey. And again, some of you have very different backgrounds in acid base, from having a full year of intro college chemistry, and this might be very simple to you, to others who have never seen an acid or a base defined before. So I'm going to come at this with basically those students in mind. I apologize to all of you who already know all these answers, but kick back, relax, have some popcorn, and enjoy the ride. So an acid-base reaction, just to get clear, there are two possible definitions for an acid-base reaction. This is the most popular one that we're going to use. It's called a Bronsted-Lowry definition, and it focuses on the fact that any compound that donates an H+ is designed to be an acid. So anything that is a proton donor, and a proton is something like H+, all it is the nuclei on hydrogen, no electrons. So something like HCl, you might have heard of hydrochloric acid, is something that could be an acid because it has a hydrogen that it could give up to produce an H+. Okay? The base, on the other hand, would therefore be a proton acceptor, an H+ acceptor, and therefore it would need a lone pair of electrons, like our Cl- could act as a base. And so this is Bronsted-Lowry's definition. Taking an up close look at it, in every acid-base reaction we are going to see, the key is that there will be these equilibrium arrows, because every time you do an acid-base reaction, you will generate a possible acid-base pair, which we label as conjugates. Now, in equilibrium, our goal in this acid-base land is to be able to determine which way the equilibrium lies. Does it favor the product side of this acid-base reaction or the reactant side, meaning it doesn't really want to act like an acid under these conditions? So this is what I want you to keep in mind. At some point, we are going to have to look at both acids in this reaction and ask who is the stronger acid, or look at which one is the stronger base. And this will dictate the direction of this equilibrium. But no matter what, the terminology will always remain the same. The products will always be known as the conjugates. So notice this is the conjugate acid, because if it donated and lost a proton and went in the reverse direction, it would be acting acidic. Yet you can see on the other side, if it wants to go forward, it would have to pick up a proton and therefore act as a base. So every species that can act acidic has its conjugate base, and every base has its conjugate acid. Welcome to the language of acid-base land. I'd like you to pay attention here, though, that we're not leaving these, we're still pushing electrons. So notice they're still using these arrows to show the electrons going from the lone pair to the hydrogen, and that this HA is not actually losing H+, but it's H+ is being ripped off by the base. Okay? The other definition is the Lewis definition for acid bases. This is one that's less likely to be used and less familiar to even those who have dabbled in a little acid base land before, but I'll show you in a second how it is very relevant to our Orgo land. So this just flips the Bronsted-Lowry acid base on top of its head. Instead of looking at a proton donor as the acid, it focuses on the base. So here you can see the very first thing I'm mentioning is the base for the Lewis definition. that a base has an electron pair donor, and therefore it's just searching for an empty p orbital, a positive charge of some kind, and any positive charge species that this reacts with would be considered an electron pair acceptor. So this would be H plus would be an electron pair acceptor, and this is why we'd call H plus a Lewis acid. So you're wondering, why do we need this new method and this new definition if H plus is an acid in Lewis as well as in Bronsted-Lowry? And it comes to this point here, that there are certain molecules that we will play with in Orgo land, especially, for example, that have pairs of electrons like in that pi bond that could be willing to donate that pair of electrons. Its ability to donate those electrons makes it a Lewis base. And then we look at this strange looking little thing, this BH3. It's only got 6 electrons around it, which means it has an empty p orbital. That is, and that's a very ugly p orbital, sorry. An empty p orbital that is ready to accept a pair of electrons. And it could come from OH minus, or it could come from this pi bond. So, glimpse of the future, we will see Lewis acids and Lewis bases in our Orgo world when we have BH3 reacting with our pi bond to open it up and therefore react and create this positively charged carbon, which won't stay there very long. It will then look for another Lewis base or a Bronsted-Lowry base or some source of lone pairs to make a fourth bond on that carbon. Okay, so that's a little glimpse of the future, and we're not going to play with Lewis acid bases much, but I thought you should see it now. So here is the overview, and you notice how I even put down there right below us here. I think I got my directions right after last lecture. I was like, whoa, where am I going? Okay, I think now I definitely know it's just below me is the little teeny words for Lewis, because we're going to pay less attention to them, and we're going to focus a lot on this piece here, which describes an acid as an H plus donor, proton donor. Okay, cool. Now, we talked about strengths of acids, and therefore there is a new way to measure them called pKa's, and some of you may be familiar with this, others not. So let me give you a very brief overview of what a pK is, but it's actually a measurement in lab to help us understand the different relative strengths of acids and how willing they are to give up H plus. Who wants to just give it up easily? And who does not want to give up H plus? This would help us define the acid. So here's a reaction, and we talked about HCl already, hydrochloric acid, and kind of what its premise is. It already sounds like an acid. So let me use it as our poster child for what a strong acid's pKa would look like, and what does that mean? Well, as we mentioned, this reaction is in equilibrium, and therefore any equilibrium reaction is going to produce an equilibrium constant expression, products over reactants. And therefore, if I really want to know, does this reaction, is it favorable in this direction? Does it really want to produce products? Then we know the equilibrium constant should be very high for this, greater than 1. But in our acid-base world, there's something that's so abundant in this formula that we think it's a constant as well. In our aqueous solutions, water essentially has a 55 molar concentration, which is just so much higher than any of these other species in the formula that it remains constant throughout this entire equilibrium process. And if it remains constant, then let's pull it out and add it and multiply it to, multiply it times the equilibrium constant and create this new expression known as Ka, which looks at only the species that are involved in this process that really relate to the acid and its conjugate base. Okay. Notice also we have H3O plus here, but you will also see this essentially, I could write this as H plus Cl minus. Okay, so HCl going to H plus Cl minus. Which way does this equilibrium lie? We could look at the equilibrium constant expression and get a value. The value for this is 10 to the 7th, 10 million times more product than reactant at equilibrium. That's pretty large. That means this wants to make product a lot. And therefore, if we were just to use Kas all the time, we'd be using these exponents, 10 to the 7th, 10 to the 8th, 10 to the 5th, 10 to the minus 3rd, 10 to the minus 4. All those exponents are confusing. So what they've done is they have now decided the best way to get rid of exponents is to take the minus log of these values. And when you take the minus log of these values, you turn all those exponents into whole number integers or integers of some kind or another. No longer using exponents. So this is the new scale we will use, that we will try to define every acid-base reaction as a pKa for an acid. And we can then compare the pKa of this HCl as -7 compared to the pKa of water. How easy does water want to give up its H plus or other molecules? Okay, so keep in mind, just to make sure we're clear about this, this reaction really wants to go in this direction because of this huge equilibrium constant. And therefore we have a strong acid. It really, that's the definition of a strong acid, something that wants to give up H plus very well, which means its base over here, its ability for Cl minus to grab and fall in love with an H plus is very, very low. Cl minus is happy, even though it has a formal charge. It's very electronegative. It's very far to the right on the periodic table. It is happy being Cl minus. So if it's happy, why would it want to react? Where HCl is grumbly bumbly, I'm strong, I don't want to have this H attached to me here, go away H plus, and off it flies. So these are definitions for strong acids and things that are very reactive versus weak conjugate bases, which are stable. Sorry for the writing over the stable part. Okay, keep this in mind. This is a very big key to our process because we may focus on acids a lot in this process, but it'll always be telling us something about their conjugate base as well. That a strong acid has a weak, unreactive conjugate base. So think of weak as non-reactive. And strong as ouch. Painful, wants to react. HCl will hurt you, for example, if you put your hand in a beaker of concentrated HCl. Don't ever do that. Okay, so let's look at some more compounds and see what their possible pKas are to get a sense of relative strength of acids. This is ethane. We'll be talking about functional groups in lecture 4 so that you would be able to write this as ethane and know and how to speak orgo very soon. How willing is ethane to give up H plus and go through this equilibrium process to produce its conjugate base, the C minus? So again, we can look at the equilibrium expression. We can translate it into a Ka that takes the water out into a new constant. And now all we're looking at is the ability for ethane to give up H plus. And does it like to do this a lot? Then I'd expect a big product number and a very little. So I'd expect a big number over 1. If it doesn't want to do this, I'm going to get a little number less than 1. Experimentally, it's found to be 10 to the minus 50. Minus 50. That's 0.00047 more zeros on a 1. That is a very teeny number, but it's hard to envision 10 to the minus 50. So let's take the minus log of it. And now we have this huge number of 50. So believe it or not, the larger the pKa, greater than 0, the worse your compound is at being acidic. Negative pKa's, like -7, mean that you have a very strong acid. Ouch. Okay. So this means that the actual conjugate base, oops, let me see if I can erase that up there. This is a technology. Cool. Get back to our, so this means that this reaction really wants to go in this direction and favors staying in the ethane molecule. So that's a very weak acid. Doesn't want to give up H+, which means, you know, it's happy here. Let's just keep it here. Because as soon as you pull an H+ off of it, it gets very uncomfortable. I'm C-. I'm a negative formal charged carbon. I do not like negative charge. I'm not electronegative. I'm very strong. I'm very reactive. I'm not as stable as my original. I'm ouch. Yikes. Okay? So even knowing that you have a weak acid means you can tell something about its conjugate base. They come as a pair. Pretty cool. And so we're trying to develop ideas about reactivity so that we know if we ever put two molecules together, who is going to be more acidic, who is going to act as the base. That's the goal. Oops. Okay, so here's our summary. Summary for acids and bases with my poster child of HCl up there. And keep in mind the equilibrium always favors going to the side of the reaction that creates the weaker acid and the weaker base. These are the happier things. They like hanging out together. Okay, so strong acids are very bad and reactive. They can't wait to go make their weak conjugate bases, and they will have lots of negative pKa's. Where weak acids can't wait to take their strong conjugate base, grab a proton, or stay as weak acids and not give up their H+. So this is the game we'll play as to determining the strength of their acids and bases. And now here's an overall summary chart of the kind of groups you're going to see in Orgoland. But again, starting out with our popular little HCl, notice it's way down here at like -7. Okay, and then our ethane, which was way up here at around 50 for its pKa. And now there's all these other functional groups that are in Orgo. And what I'd like to do is just highlight quickly, this is a carboxylic acid. This is one of the, you can even hear from the name, it's slightly acidic, but definitely with a pK of 5-ish. It's not as acidic as hydrochloric acid, and you drink carboxylic acid sometimes. They are the main component in vinegar. So if you're having oil and vinegar dressing, you're having carboxylic acids all the time, and the worst thing they can do is give you a little acid indigestion. Ooh, okay, but other compounds that you'll see a lot, these are phenols. They're up there on my list. Functional groups, you got your Post-it notes yet? Woohoo! Keep getting those Post-it notes. You should spy these. And then you should be able to spy what this functional group is, ROH. It's very similar to water, as you can see right here, HOH. These have a pKa of around 16, and therefore are considered basically up here on the neutral side. They're not weak acids, considered acidic at all, right? What is this functional group? Yes, you got it. They're alcohols. Alcohols are neutral. Only phenols and carboxylic acids are weakly acidic in our list of special functional groups up there. And if you notice, that's why I only wrote those two functional groups with red ink to express red for acid. That's also what the pH vapor turns. Cool. This is the theme of the overall day. Keep in mind, strong acids have weak conjugate bases. Strong bases have weak conjugate acids, and vice versa and so forth, right? Cool. Give this one a shot. Stop. Okay. Are you ready? Which combination of reactants below will not form any appreciable amounts of product? Weak and weak will never react to form strong and strong. So this is the least favorable kind of reaction you want to set up, where you put reactants that are both weak acids and weak bases. So this would be something like putting in water and ethane. Nothing's going to happen. So that's the end of our overview of what an acid and a base is. Very quick, especially if you've never seen one before. So please feel free to review this, ask me questions about it. And then in lecture 3B, we're going to go in and see what makes a really strong acid. For example, why is HCl such a strong acid? Why is a carboxylic acid a little better at an acid than an alcohol? This will be important for us to rationalize, so you don't have to memorize the pKa table. You will always be able to rationalize why something is a good acid and something else is not. Okay? See you soon. Bye.